Number 13, does this series converge? What I'm going to do next is unnecessary, but I like to get to know a series before I use the integral test on it. So I just want to see what this looks like out of curiosity. All right, that's it. Oh, time to apply the integral test. First, can we apply the integral test? Here we go. We start with defining our continuous function on this restricted domain. The easiest checks, f is definitely continuous because we're never dividing by 0. There's really nothing to justify here. It's an easy check. For the next two, is our continuous function always positive? Well, the denominator certainly is. What about the numerator? At this point, you might take a look at the graph of the inverse tangent. You don't remember what it looks like? The graph tangent. Tangent in the domain where we restrict it for the arctangent looks like that. And the arctangent looks like this. And so for x values greater than or equal to 1, our arctangent values will always be positive. Therefore, our function will always be, for this restricted domain, positive over positive, which is positive. This condition has been met. Finally, is our function decreasing when x is bigger than or equal to 1? Well, we can see that as x grows and grows and grows, the numerator is just approaching pi over 2, while the denominator is growing very fast. So clearly, these terms are going to 0 and getting smaller and smaller and smaller as x gets bigger. But let's go ahead and find f prime and show this very decisively that it's decreasing. The derivative of the numerator multiplied by the denominator minus the derivative of the denominator times the numerator, all divided by the square of the denominator. This simplifies to 1. So here's our first derivative. The question is, will it always be negative? So let's ask that question. Will it always be less than 0? We can multiply both sides by this positive denominator. Isolate the x components. And if we just substitute x equals 1 in here, we have 1 arctangent of 1, which is pi over 4. So 1 times pi over 4 is just pi over 4, which is, about 3/4, a little bigger than 3/4, which is bigger than 0.75, which is definitely bigger than a half. And this just continues to grow, so this is definitely true where we need it to be true, and therefore all of our conditions of the integral test have been made, and we can do the integral test now. Since our conditions were satisfied, the convergence or divergence of our series will mirror the convergence or divergence of the definite integral of f of x as x goes from 1 to infinity. You might be able to just do this one in your head, basically the u substitution. If u is the numerator, then du is dx over x squared plus 1. So we have the definite integral of just u du. And if x starts at 1, then u starts at inverse tangent of 1, which is pi over 4. And as x goes up to infinity, u is approaching the arctangent of infinity, which is pi over 2. Recall the graph. And now we don't have to deal with the improper integrals. So we get this result, which is clearly a constant. Let's see, pi over 2 squared is pi squared over 4, so pi squared over 8, minus pi over 4 squared, which is pi squared over 16 divided by 2, so pi squared over 32. And so since this definite integral converges, so does our series by the integral test. And that's how we do number 13.